So let's begin class. So welcome back after having a little bit of time off there. So for today, you needed to examine subsections 6, 7, and 9 in section 3. And so let's just do a little bit of a review over that material. And again, the reason why we do these, or why I start off with a little bit of a review here, because this helps me show you what I think is important from these sections, and especially when you are studying for tests, take note of that. Also, this will help you maybe trigger some ideas for questions that you might have had from examining those particular subsections. So in these notes, in the videos, you saw finally the full statement of an ARIMA PDQ model. These models are used throughout time series analysis, and as we go throughout then the rest of the semester, we will look at various generalizations of these kinds of models. So for example, we will look at particular situations where maybe we have in addition to observing x of t, maybe we have something that we can think of as an explanatory variable as well, and we can include that in the model. We'll look at situations where maybe we can no longer assume, let's say, the variance is constant. How can we also simultaneously model the variance as a function of time in one of these models? And so there's many other extensions as well, but those are two of the primary ones that we will examine as we go along. So this is what the model looks like. It's not your standard rigor regression model that you would see in every or most other stat courses out there. And so what we have here at the very beginning is that we have this autoregressive operator, which we call phi of b. Then we have the part that allows us to do differencing, to take care of non-stationarity in the mean. Our variable of interest is x. It's indexed by time. So that's the subscript t. Then we set that equal to our moving average operator times wt. Wt is our random variable that denotes what's called white noise, meaning each of these w's indexed by t are independent of one another. They have a mean of 0 and a constant variance. And so with this setup here, what we want to do is estimate all the corresponding parameters in the model. These phis, the thetas, and also sigma squared. Okay? Now, if the mean of the series, so the expected value of x of t, if that's not equal to 0, and also d is equal to 0, meaning we have no differencing, we have one more thing that we need to deal with in this model. And we can rewrite the model now with this additional term, which we denote by alpha. All that alpha is equal to mu times 1 minus phi 1 minus phi 2, all the way down to minus phi sub p. That's all it is. And so anyway, essentially what this does, it allows us to estimate mu, because mu is not equal to 0. In most applications, mu will not be equal to 0. And when you don't have differencing, we need to estimate it. So if we have differencing, why don't we have to estimate it? Anyone remember why? So first differences will look like this. Okay. What's the expected value of that? 0. Okay. That's why. Now, okay. Specifically for these subsections. Now, so subsection 6 allowed us to put together a lot of the stuff from subsections 1 through 5. We spent a lot of time talking about the ACF, some time talking about the PACF. And the reason why we do that is what we're trying to do is match what we would expect an ACF and PACF to be for a particular ARIMA model to what was actually estimated for the ACF and PACF. Because that leads us then to decisions about, okay, P must be this, or Q must be this. And so that's why we spent that time doing that. And in the end, we have this nice little table here that kind of summarizes what's going on. So if I have a purely autoregressive model, meaning Q is equal to 0, then what we would expect to have happen is that the ACF will tail off to 0. The PACF will cut off to 0 after lag P. So what that means is that you're going to have something that looks like this. So here's lag H. We'll just call this the ACF, or the autocorrelations on the on the y-axis. And so one potential way that this could look to be tailing off is, is something like this. Okay, that could be a tailing off. Another tailing off could look like this. Another tailing off. It's probably going to be a little bit harder for me to draw. Maybe like a sine cosine wave. Those are common, I guess, ACF, or what these ACFs commonly look like when we're talking about tailing off. Okay. The key aspect is that over the lags, eventually these autocorrelations tend to go to 0. And notice that the sine cosine part here, we see some, relative to where 0 is, we do see some, it's decreasing towards 0 here, but then it's increasing a little bit. But over all the H's, we can see eventually we're getting closer and closer to 0. Okay? So that's what one of these plots will look like. This is for the true ACF. Then if I take a sample, my estimated ACF then should look something like that as well. Again, for a particular model. Now for the PACF, lag H, partial autocorrelation function, let's say if P was equal to 2, I might have something that looks like this. And that's it. Notice that at lag 2, that partial autocorrelation could actually be a little bit higher. Or farther from 0, potentially. But the key is that after lag 2, it's essentially equal to 0. And so that's what, let's say, maybe the true PACF might look like. Now, for a estimated PACF, maybe you might have something that looks like this. Okay? We have some, let's say, non-significant values after lag 2. So they're within the, those dotted lines that you typically see on the plots. And if I saw something like this, I would say, yeah, I think an AR2 model would be appropriate for my data. If I purely had a moving average model that was appropriate for my data, I have essentially the opposite occur in terms of the ACF cuts off to 0 after lag Q, and the PACF tails off to 0. Then what makes things complicated, though, is when both in ARIMA, or both when P is greater than or equal to 1 and Q is greater than or equal to 1, meaning I have an ARIMA model. And basically what happens is that we have a combination of these cells that leads to tailing off to 0 after lag Q for the ACF. Why? Well, cuts off to 0 after lag Q. So that means I'm going to have at least Q different lags where I have some non-zero autocorrelations. But since I also have the autoregressive part too, I'm still going to have some more autocorrelations after lag Q. And they should follow the same pattern that you would see for just an AR model after lag Q. That's why this occurs. Then for the PACF, we combine the two to get what we would expect for an ARIMA PQ. So these are the characteristics that we would expect to occur. Now, as you might expect, for a sample itself, depending upon what your sample size is, it might be a little bit difficult to figure out, is this pattern occurring or not? Also, what makes it difficult is actually deciding when is this tailing off to 0 actually occurring? Is it lag 1? Is it lag 2? Is it lag 3? It can be difficult to make that decision. And so this is where you can get a lot of experience yourself by taking advantage of the tools that I presented in this section or subsection to simulate some data. And that's the cool thing about simulation. You know what the correct answer is. Let's take a look at what happens if I had a sample size of 100 or 200. Let's simulate multiple time series. Let's look at the estimated ACF, look at the estimated PACF, and compare it to what the true value should be. And that gives you some experience to see, okay, there can be at times some questions about, what is P, what is Q, but it's also dependent upon what the sample size is. So in the end, what this table essentially gives us then is some ideas of what potential models could be. And as we go along in this section, what you'll see is that eventually we'll get to a point where we can say, okay, I think this model might be appropriate for what I see for the estimated ACF and PACF. I see maybe perhaps this model might be appropriate, this model might be appropriate, so that you have a set of candidate models. And then through some tools that we'll be looking at in the next few weeks, we can then narrow down between these candidate models and choose one model overall. So a simple question, well, hopefully a simple question for you. Is it easier to choose P and Q for a large or a small sample? Large. Because I have more evidence. I have more information about what's going on. And this is, the same with any other kind of thing that you do in statistics. You want as large of a sample as possible because that gives you more information about the population. And then you can make better judgments. Same thing here. Okay. Subsection 7 then introduced the I in ARIMA. Allows us to do the differencing in the end. And then lastly, subsection 9. Finally, we get to a point where we can actually estimate a model. We will focus on maximum likelihood estimation because this is what's primarily done in time series analysis is use maximum likelihood estimation. There are other estimation techniques out there. Excuse me. They are used much less nowadays. If they are used, especially what's called conditional least squares, CLS, it's used basically just to get, let's say, initial estimates for the maximum likelihood estimation estimation routine in terms of what you would learn in Stat 883 or Stat 880. You learned how to derive maximum likelihood estimates in a closed form situation. We can't do that here. Instead, we have to use numerical iterative methods to find what these estimates are. And to do that, you need to come up with a starting spot, like an initial phi1 or initial theta1. So you can put it into your estimation routine. And Conditional least squares is one way that's used to do that. Without going to all the details behind it, as you can imagine, least squares. So it's something like what you will learn in a regression setting, where you first learn about least squares. It just gives you a place to start to get the maximum likelihood estimates. You are not responsible to know what any of these particular methods are. I don't think it's worthwhile, and we don't have the time to go into them. Now, fortunately, there's a nice function R called ARIMA that automatically does this numerical iterative method for us to find the maximum likelihood estimates. Be very familiar with how to use that function, how to deal with the corresponding arguments in the function. As we go through the semester, we'll learn about more arguments that we can use with this function as well. Be very, very careful with estimating alpha and then mu. Unless there's differencing, we will always want to estimate alpha or equivalently estimate mu. And unfortunately, the output that's given by ARIMA is not necessarily clear about what that estimate is. I think, to be honest, I wouldn't have labeled it as it is given. Also, then we want to do inferences, meaning we want to, let's say, come up with a confidence interval or do a hypothesis test for these parameters that we're estimating, like phi1. And also in this set of notes, there was another discussion about understanding how R works in terms of method functions and generic functions. So do note that this ends the test number 1 material. Okay. Now, we will have another Tuesday class before we have test number 1, but that material will not be on test number 1. It doesn't mean you should put off not looking at that material as we go along. It's not going to be on test number 1. Okay, so with that was a brief review. Are there any questions regarding the corresponding material? Okay. Yeah.
I'm confused for the ARIMA PQ when you say tails off to 0, especially with the ACF, if you don't mind coming back
Yeah.
to the so when you say tail off to 0 after that Q for the ACF, do you mean, especially when we have this like cosine and sine function, do you mean that that Q is the Q the closest lag to 0, or is it the one that the first lag that is below the significant line?
Well, let's do a plot. So let's say that Q is equal to 2. Okay. So that means that I might have something like this. Okay, at least. So that second line is at 2. Then I might be having something that looks like this. Notice after lag 2, it's kind of getting closer to 0. So that's what that would mean. Other questions? And let me just emphasize, it's often not easy to figure out what P and Q are. This is just one tool, the main tool that people use to make that determination. And you will often say, I can think of multiple models. That's why specifically, I think it was for the earthquakes data in project number 2, I asked you to suggest 2 potential models. Okay, so last week I was in New Orleans at the Conference of Statistical Practice. And so one of the presentations that I attended was someone was presenting on cherry blossom prediction in Washington, D.C. For those of you who may not know, in Washington, D.C. every March now, right around where what's called the tidal basin on the mall area of Washington, D.C., there are a number of cherry trees that were given to the U.S. from Japan about 1910 or so. And it's a big thing in Washington, D.C. They actually have a festival associated with this when these trees are starting to then bloom at the beginning of spring. And it's a big thing to figure out when are these cherry blossoms going to come out. In the end, it's a very, I guess you could say, pretty thing. This is what it would look like there. And as you might expect, because of global warming every year, it seems to be getting earlier and earlier and earlier. And so this individual who was giving the presentation, he was using an ARIMA 212 model to do the prediction. I have a copy of his presentation. I have contacted him to also obtain the data. And so it would be really cool if we could play around with his data some in our class, and hopefully he will give it to me. He said that he needed to get special permission from the university to release the data. I can understand if this is maybe human subjects data. I don't understand why that would be for cherry blossoms, but that's what he said. I've been waiting, I think, saw the presentation on Wednesday, and I contacted him shortly after that, and I'm still waiting for the data from him. Okay, so project number 2. So a reminder that it's due on Thursday at 8 p.m. Again, when you turn it in, email it to me. Make sure you copy all your group members on the email, and also make the file name the last names of all your group members. We've basically talked about all of project number 2 already. The only thing that we hadn't, I guess, talked about was the estimation for the earthquakes data. Now, after doing subsection 9 in my notes, this should be relatively straightforward. Use the ARIMA function. Estimate a model as P equal 1, Q equals 0. I'm sorry. P equal 1, D equals 0, Q equal 1. Okay. Make sure you include alpha in your final answer, your alpha hat, I should say. And also, do the corresponding hypothesis test for the parameters that we're estimating. Were there any last questions about the project? Okay. Let's take a look at the schedule web pages, see what's coming up next. Well, I just had it open, and unfortunately, I must have closed it. Okay, so we're week 7 now. So we're about halfway through the semester. Next week, of course, is spring break. So we don't have class. Then that first week coming back from spring break is week 8. So we will do subsection 10 for that Tuesday class. This is not meant to be as much material as we would normally cover for a Tuesday class. The reason being is because then on that Thursday after spring break is our test number 1. After that week, we will only do one subsection as well for that Tuesday class because, again, of that test. So that's I reduced the amount of material there. Subsection 10 and subsection 11 are on forecasting. So at the beginning of the semester, I said one of the ultimate goals for time series analysis is to forecast the future. And so this will teach us how to actually do that. With respect to these ARIMA models, and what we see here will extend to other models that we will have as well. So, since that test is coming up, and since we haven't had a test yet, I want to talk a little bit about the test structure. That Tuesday class after spring break, we will review a little bit of what I'm talking about here, but we will spend most of the class period reviewing the material for the tests. But here today, I want to talk about the test structure because for many of you, this structure will be new. If, though, you ended up taking Stat 873 with me, it is going to be the same format. So the material for the test is up to maximum likelihood estimation. That's subsection 9. This is going to be a closed book, closed note, closed video test. So you cannot use any of my notes to help you take the test. If you took Stat 875 from me, that is different from that. You cannot, of course, talk to classmates during the test or anyone outside the class during the test. The test will be done in this particular room here. You will be using the computers that are on your desk here. So it might be a good thing to do at the end of class if you have time. Log on to the computers just to make sure you can. It is the normal university login. Log on to the computers. Make sure you understand what's available to you. Our studio is on all of these computers here. Now, what you can use during the tests is you can use any of my R programs that are on my course website. There is also, what I posted since our last meeting, I believe, I posted to the graded webpage an equations sheet as well. That gives important equations that we've had during the semester. Actually, this equation sheet is meant to be for the entire semester itself. I just thought it was easier just to construct it all for the entire semester. And you can download it here. You can look at it during the test. Also, you can look at then the corresponding R help that's available within R Studio or within regular R itself. So that's what you have access to. Now, why do I use this format? This is a format I've used for many years for most of my classes. The reason being is because obviously I want you to make sure that you know the material. So that's why it's closed book, closed note. But I don't want you to have to memorize R code. I don't want you to have to memorize equations. But especially the R code part, think of it the way that typically people, write R programs. Let's say you have a data analysis that you need to do, and you might be thinking, I did something like that before. I'm going to go back to an old R program that I had, copy, paste some of that code into my new program, make some small changes to it, and then use that for my data analysis. And so what this test format does essentially kind of mimics that approach. It allows me to assess your ability to use R, but without you necessarily having to memorize code. Okay? So, of course, there can be computer problems during an exam. I think I started giving these kinds of tests about 18 years ago for not necessarily this class, but all other classes that I've taught. And that's one of the reasons why I like this classroom is because we have these computers here. And I rarely have run into computer problems. But it can happen. So obviously, if you have a computer that's not working for you, well, we have other computers that are available. We have a small enough class for that. But if you want, you can bring your laptop and use that only as a backup and promise me that you're not going to look at anything that you shouldn't be looking at on your laptop, like my course notes. Okay? So think of it that way. Always think of having a backup. Make sure that you're saving your exam because as I will say shortly, I'll be giving you a Word file. Make sure you're making sure that you're saving the Word file as you go along during the class. You don't want to go 45 minutes and not save your file and realize you accidentally just closed out Word and you just lost all your work. Okay, so always think of having backups available to you. Make sure that you after you get done with the test, email yourself the test to make sure that you have a copy on your of it as well. So the tests will start at 9 a.m. At the very beginning of the semester. If you remember, I asked all of you, would you be available to start a half hour early? And everyone said yes. So we will start at 9 a.m. We will go till 10:45. At least that's when I will say it's time to turn in the tests. If it takes you 5 or so minutes after that to turn in your test, that's fine. I am 99% confident that there's not another class in here after us. And so I don't think we'll run into any problems with another class trying to get in. Now, the test is written, though, to be 1 hour and 15 minutes long. So I'm not going to take advantage of this extra time to make the test longer. It's meant to be 1 hour and 15 minutes long. The tests at 9 a.m. will be made available to you on my graded webpage on my course website. So about 8:59, I'll say, okay, the test is available to you on my website. Go ahead and download it. And so you'll be able to download it to the computer that you're using here. I might have a few announcements about the test, and then you'll go ahead and start taking it using the computers here. Again, it will be a Word document. That Word document is where you need to type in all of your answers. When you are done with the test, to turn it in, you simply email it to me. Do not leave the room until you receive a confirmation from me that I've actually received your test. If you happen to use Gmail as your primary emailer, what I've noticed is that it could be some of the settings in Gmail that some people set up. Gmail will actually delay sending it to me. It will often take 10 more minutes for me to get it. It won't be at the speed of light as you would normally expect. So I recommend that you don't use Gmail, but if you do use Gmail, it may take me longer to reply to you to say, I've received your exam. Again, all answers go in the Word document itself. So what you're putting in there is similar to what you do for a project. I want to see all our code. I want to see all our output. I will frequently copy and paste your R code into my own program and see if it runs. And so essentially by always showing me your R code and output, you're giving me proof that you've actually done it. You're showing me your work. This can be very, very important then if by chance you need partial credit because maybe you made a mistake someplace. I can look at that and, let's say if the model that needed to be estimated was, let's say, an ARIMA 101 and you accidentally estimated an ARIMA 100, but you did everything else right, okay, you're going to get most of the points for that problem. But if instead you only show me what that final answer was, it's hard for me to maybe know how you got that, why you chose that model, and you would receive less points. Now, obviously we deal with various mathematical equations in our class. For the projects, I've said that you need to use the correct notation when you write out a model. For tests, because of the time constraints and because I know that some students are not maybe as comfortable with the equation editor as I am okay if you use, let's say, a text-based equivalent to using an equation. What that means is, for example, let's say for some reason you needed to put phi1 on your test. It's okay for you to write out phi_1. Underscore meaning subscript. Or I would even take phi1. So that's okay. But I encourage you to use the equation editor if you can. On the tests, you will notice that obviously I will be using some of these symbols. So if you needed to put Phi1 in your answer and you saw in the question for the problem, Phi1, well, just copy and paste that into your own answer. In fact, I believe I made up the test I finished making the tests about a week and a half ago. And there is a derivation, at least one derivation on the test. And I purposely put in some of the mathematical symbols that could be useful for that derivation so that you can copy and paste it yourself. On the tests, you will need to derive an autocovariance function. I guarantee it. It is there. And, that will take a little bit of time to do. And so because of that reason, the number of points that are going to be, that this particular problem will be worth will correspond to that. But do note that you will need to derive an autocovariance function. There will also be at least one data file that you will need to download as well. So that you can maybe, let's say, like estimate a model or estimate a PACF or something like that. Now, when I constructed the exam, the first thing of what I did was I went through every single quiz question that I've given so far, and also all the projects so far. And for each part of the project, each quiz question, I wrote down this problem. Well, I didn't say it that way. I said estimated ACF or derive ACF or whatever. What was the main purpose of that problem? That's how I started figuring out, okay, what do I want to assess on the exam? The reason why I am telling you this is because I thought after I got done doing that, I thought, that would be a good way for you to start studying for the exam. Go through every quiz question, go through every project question, write down what the main purpose of each one was. And then when you're studying, make sure that you understand how to do then each of those aspects. Now, that doesn't mean that I'm going to always ask you a question exactly the same way as it was on a quiz or a project, but I could assess you regarding that kind of material. So now for our next Tuesday class that we will have, again, we will spend a lot of it just reviewing for the exam, in particular reviewing the corresponding material for the exam. Please, please, please bring questions that you may have. I will make sure that I stop early this review and what I had to talk about in the class so that you have an opportunity to ask questions if you have some. At this time, though, are there any questions about the format for this exam? At least for my tests, I feel as though that they are, let's say, fair tests. I'm going to focus on stuff that you've seen in other places, seen during our class. At least I feel as though I never, let's say, pull something and put it on the test that you've never seen before. I don't think that's very helpful. Do note that I do not ever scale grades. I've never had to do that in my career. I don't plan on doing that right now. The grade that you get on that test is the grade then that will be counted towards your overall grade for the course. Okay, so let's go back to this COVID-19 example that we've touched on a few times already in class. The purpose of us doing this is to give you some more experience with the material that we are talking about in our course. But also, the nice thing about this is that this is something that's obviously very relevant right now. And so what this example dealt with, again, was wastewater monitoring. And we want to see how much of the SARS-CoV-2 is in the wastewater. And this is the plot that I've shown you before over time. for in Lancaster County for the wastewater monitoring. So the x-axis is time, the y-axis is the amount of the virus that's in the wastewater. I suppose I closed that out. Yes, I did, unfortunately. So this went up to about the end of January right there. And I was preparing for today's class. I was looking, well, where are we now? And essentially, we've been kind of going like this. And so relatively speaking, we seem to be kind of higher than what we've been at, let's say, during this time period or this time period here. And unfortunately, things aren't, let's say, decreasing. So, unfortunately, I have that there already. If I didn't have that there, do we have stationarity, based upon this plot? And so, again, we're looking at in terms of the mean. We're also thinking in terms of the variance, covariance as well. And, what do we look for here with respect to the mean? Do we think that the mean is changing over time? We don't know what, let's say, mu is, but we can see what kind of a general estimate might be by looking at the observed data here. And what we see in this plot definitely is that we have this huge spike that really stands out. Note that though, there wasn't really for that many time periods though. So that's something to think about there. We also have a few other points in the time series where maybe we're dipping down a little bit lower. And so I think from looking at this, stationarity with respect to the mean is questionable. But, imagine, let's say we didn't have these points at all. Would that change your mind about stationarity in the mean? It might a little bit. And so that's why, and given that this was for a short time period, that's why I think it's questionable. Now note that, the first time that I saw this particular plot, I immediately thought that a particular kind of time series model would be helpful. One that basically was ARIMA, but was one of these extensions, referred to what's called a threshold model. And what a threshold model is basically, once you get to a certain point, things tend to blow up. And that sometimes can happen, especially with disease-related data sets. Imagine, infectious diseases. And so that's why I immediately thought of. We'll see if I taught that before. We'll see if we can, but I often do not when I teach time series. We'll see if we can fit it in. And so what that would basically means is that everything is, let's say, normal, essentially stationary, except for when you hit a certain threshold, then you're no longer stationary in the mean, and there's ways to take care of it other than differencing. So that's what I immediately thought of when I saw this data. What do you think about variance or covariance here? Do you think we have stationarity just from looking at this plot? The key is, obviously, we have more variability here. Maybe a little bit less variability here, maybe a little bit less variability right there, comparatively. What would be nice, and maybe I should have done this, is if I could have, let's say, zoomed in, let's say, put this as my maximum value on my plot, so I could look better at some of these, lower values there. And so it, again, is questionable. Do we have stationarity with respect to the variance here? Okay, let's see here. Well, let's look at, and some of this is actually from week what we would have done in week 5, and I had hoped that we would have got to on week 5, but we didn't. But let's take a look at the estimated ACF, which we've seen before, and the estimated PACF. Okay. Does the ACF have the characteristics that we would expect for non-stationary in the mean issue? Yes or no? Well, if we had non-stationarity in the mean, what would we expect this plot to look like? There's going to be a lot of high autocorrelations. We would expect, basically, something, if you follow where my mouse is, we would expect this to look something like that probably. And so this plot does not have the characteristics of non-stationarity in the mean. Now, when we do see this kind of trend, where my mouse is right here, this primarily corresponds to particular cases where you would have, let's say, a time series that looks like this. Okay? That's where definitely you would expect the estimated ACF to have this long, high autocorrelation pattern. We obviously do not have that here. And so this is something good to take note of, that, if we do say that we have non-stationarity in the mean here, the estimated ACF might not have this typical characteristic that we would associate with it. So something to take note of. It's not something that I unfortunately have in my notes. Okay, let's go back to the plot. So what does this estimated ACF, what does it look like it's doing? Think of that table that we saw earlier. Or maybe we should look at the PACF. This is a little bit easier one. What's the estimated PACF doing? Yeah, cutting off to 0 after lag 1. And then the estimated ACF, what's it doing? Yeah, thank you. Tailing off to 0. Okay. So what this is telling us is that perhaps an autoregressive 1 model, or in other words, an ARIMA 100 model, will be appropriate. Now I'm going to hedge on that because I am worried about the variance. If we have non-stationarity in the variance. And so, I'm not totally convinced that I would immediately go to that. But let's take a look at what first differences might look like here too. So to do first differences, of course, I use the diff function. Notice I say, with respect to lag 1, that means I'm looking at x sub t minus 1. The differences argument means that d is equal to 1. So here's my first differences. I'm putting into an object called first.diff for the lack of a better name. And if I just do head of x, we can see that if I take 68,100 minus 66,000, I get negative 2,100. Okay? Let's do a plot of the first differences. And this is what we get. What do you think here? What's really standing out to us?
Difference in variation.
Yeah, difference in variation. Okay? And we were a little bit worried about that, of course, with respect to the plot of the data over time. But it seems like, obviously, if you see where my mouse is here, I have some issues going on here. But we also see we have short time points, or we have some, I guess, somewhat short to medium time length points where we have little variation. And so this, this does concern me. Now, something else I want to point out here that is an issue that I have not brought up before. Okay. Now, look at my code here to plot the first differences. Plot x equal first dot diff. And so what R is going to do is plot the first differences versus an index. So the first difference is going to be plotted relative to the x-axis value of 1. The second one, value of 2. But let's look at that first difference. So I'm just going to use this simple text-based notation here. So there's my first difference, x sub t minus 1. No, that's not right. X sub t minus x sub t minus 1. And so the first time that I can compute this is when t is equal to 2. So I have x sub 2 minus x sub 1. So if this plot was done 100% correct, I need to plot this first difference versus an index of 2. Okay? So how do we do that? Now you have to use the y argument for the first differences, and then for your x argument, you say 2 to the length of x. So I get n essentially. And this is what we get in the end. And guess what? The plot looks very, very similar to what we had before, except for this point here is just a little bit to the right of the previous point. So in the end, is it a big deal if we don't get the index right relative to when we're looking at differences? No. You might be worried, well, wait a second, you're going to present, let's say if you're to do one of these plots for a report or something like that and present it, don't you want to have that index right? You typically would not put a plot of the first differences in a report. What you are putting in a report, let's say, or for your data analysis, is a plot of the data versus time. And as long as you get that right, that's great. We're only doing the first differences to solve a potential problem that we have with our data relative to the model that we're using. If I look at the estimated ACF and PACF of the first differences, this is what I get. So what kind of model would be appropriate here? Yeah, probably 0, 0. Now we always have to be careful, relative to our sample size here. Look how far these dotted lines or dashed lines are from 0. And just because you don't reject HO does not mean that it truly, let's say, phi1, or I guess in this case, truly if the autocorrelation is equal to 0 or the partial autocorrelation is equal to 0, you can't conclude that. But the first model that I would probably start off with is thinking, okay, just P equals 0, Q equals 0 with this data. Okay. We do have some marginally significant terms as well, or autocorrelations, partial autocorrelations.
Is there a reason why those ACF and PACF plots are very much similar?
Yeah, I know. When I first saw that, I was like, well, geez, that's surprising. But I mean, in the end, got to remember what we're looking at here. We're looking at a form of correlation. And again, when I first looked at it, I was like, well, did I accidentally draw the ACF again for the PACF plot? I had to double check. And I think, in the end, I'm not worried about it. So, but we also had some concerns about non-stationarity in the variance. So, typically, whenever we have issues with non-stationarity with the variance, one tries to handle that issue first before you deal with the mean. And and we'll talk more about this later in the semester. But specifically, this is one of the reasons why. Let me actually come up here. So, one way to handle non-stationarity with respect to the variance is using some kind of transformation. And probably the most common one is simply a natural log. Natural log is almost has magical powers sometimes to handle this kind of stuff. It will shrink the variability of parts of your data. And so if I look at a transformational log, of course, this is what I get there. And let's say if I ended up doing first differences too. Okay. Take care of the variance first, then take care of the mean. So that means I have log of x of t minus log of x of t minus 1. How could I further simplify this? Or what's another way that I can express this? Using properties of logarithms. Notice that this simplifies to that. And so we get something that's often thought of as interpretable in terms of I have a ratio between the current time point and the last time point. And especially, this is very interpretable if you're dealing with financial data. Because you're often looking at, imagine, let's say you have your stock price yesterday, you have your stock price today. If you look at the ratio there, you can kind of get a measure of, well, how much did it increase or decrease from one day to the next relative to the previous day. And so that's why, or that's a main reason why, often when we work with the log transformation, we do the log transformation before we do the differencing. It's because of that aspect. More on that later. Specifically, it will be more towards the end of the semester when we talk about models that are called Garch models. Okay, so let's take a look at what happens if I did apply a transformation. We're going to do the natural log transformation there. And unfortunately, I did not label that correctly. So let's look at a plot of the data over time. And this is what we get. So some questions for you. Do you think we have any non-stationarity with respect to the mean? Now, take into account we do obviously have some correlation in our data. Do you think I have non-stationarity in the mean? So we have a probably yes. Any other thoughts? So one of the things I focus on is notice how, and this is a kind of a difficult decision here to make. Notice how my data tends to be within, if you see where my mouse is, between these two areas. Compared to what we had before, where we had like a big spike. And then things went level, and then we had a little bit of a spike for a while, then we go down. I don't see that as much. Now, do you think the correlation, the first autocorrelation here, do you think it's positive or negative? Let's remember what a negative first partial autocorrelation means. It means that high values at, let's say, x of t are going to be associated with low values of x of t minus 1, and vice versa. Or that's what you would expect to happen, because you have a negative relationship. When you're up for one time period, you're probably going to go right back down for the next time period. And so what do those plots look like? They're really jagged. Okay, obviously I don't have that here. I tend to have kind of a, an upward trend here. Let's say larger ones are with other larger ones. Smaller ones are with other smaller ones. So, and since we see especially some upward trend that's occurring over a number of time periods, I would expect to have perhaps strong positive correlation. The most extreme, like what we were talking about before, the most extreme situation would be something like this, where I would expect to have very large positive partial, very large autocorrelation. I mean, I don't have that here, but we see some aspects of it. So from looking at this plot, I'm not as concerned, let's say, about non-stationarity in the mean as I was maybe before. So that's something to consider here. How about non-stationarity with respect to the variance? If you look across the whole plot there, we can see again where variability is in about the same range. And so perhaps this problem was solved. Okay? Let's take a look at ACF and PACF plot. That looks a little bit familiar. We see a similar pattern to what we had for the original data itself, suggesting that autoregressive 1 model might be appropriate. Now, one thing that I do see on this is that notice we have this somewhat larger partial autocorrelation here. And so if I were to, I would first look at an autoregressive 1 model with this data. But it wouldn't hurt to take a look at an autoregressive 2 model as well. So let's go ahead and estimate this autoregressive 1 model. So I'm going to put the results into mod.fit for the lack of a better name. I'm going to use the ARIMA function. It's very simple. Why didn't I do that right? Let's actually use the log transformation. The order argument allows me to specify p equal 1, d equals 0, q equals 0. Put that into an object called mod.fit. And this is what I get. Notice what phi hat 1 is. It's 0.87. Look at its standard error. If I did plus or minus 2 standard deviations, I essentially would get a 95% confidence interval. So that upper bound is going to be about 0.96, getting close to 1. If I had a value of 1 for phi 1, that would essentially mean I'm doing differencing. And so that would be concern to me because I would have non-stationarity in the mean. Or that's when differencing is used. But I'm not quite there yet. But I think what this is, the reason why I'm pointing this out is that, we have some, it's not 100% clear, do we need to do differencing or not? And we can see this through the estimation of this model. We see somewhat similar thoughts about it. So how do I estimate now alpha for this model? Okay. Well, remember, alpha hat would be mu hat times 1 minus phi hat 1. So in other words, if I actually go into, well, let's actually take a look at names mod.fit. Mod.fit is a list, and we see something called COF. That is what's called a component of my list. So to access that component, I do mod.fit $conf. And this is what I get. So that first element is phi hat 1. The second element is what R refers to as intercept. That is actually mu. It's a poor name, but that's what the name is. So to find alpha hat, I take the second element, mu hat, times 1 minus phi hat 1, and here's my model. Oh, I'm sorry, here's my alpha hat. So let me copy and paste this information. So if I were to write out my model, what would it be? I start off with a parentheses, then what? Yep. Yep. Times x of t is equal to what? We need the alpha hat. So the 1.74 plus WT. Oops. And also, because I did use the log transformation, I need to say that. And then there's one more aspect that I need to put in here. What's that? Where WT is distributed independent, normal, 0, and let's get that variance out. There we go. There's my model. That's how I state it. Let's see, was there anything else? Of course, we could do inferences for phi 1 as well, formally. You know, what's the easiest way to do inferences for phi 1 here in terms of a function in R? Use what function? Confidence, yeah. So I can do confident mod.fit, specify I want 95% intervals, and so we can see that the 95% interval for phi 1 is 0.78 to 0.96. We could do a hypothesis test as well. I put in the corresponding code in here, and you can look at it after class. I will post this to my course website, this updated COVID wastewater.R program, and we can see, as you might expect, the p-value is extremely small. Okay. So I'm not 100% convinced yet that I would want to focus on this specific model. You know, we will have additional subsections in our notes that will allow us to, let's say, compare perhaps other models to see if maybe they might be better to work with. But I wanted to go through, let's say, one model here, or justification for one model to show you that process. So are there any questions? So then what's next for our class? I'll be available for questions right after class. You do have that quiz that's due at 8 p.m. On Thursday, I will have my usual office hours at 8:30. Then at 9:30, we'll have a help class. So, you know, again, it's a great opportunity for you to come in here, finalize your project, and then if you have questions, I am available to answer those. Project is due at 8 p.m. on Thursday. Spring breaks next week, so we have no class. But if you do have questions, please feel free to post them to the discussion board. I will be happy to reply to them over spring break. Our next regular class is Tuesday, March 19th. We'll have the usual office hours before class. We'll have class at 9:30. You only need to do the first of the forecasting subsections. So subsection 10. Make sure you do watch then the corresponding video. Then the subsequent Tuesday class, we will continue with forecasting as well. For those of you who are reading the book too at the same time, this corresponds to section 3.4 of Shumway and Stouffer. We will also discuss the grading of project number 2. We will review for the tests, and of course there will be still that quiz that's due on that Tuesday. And of course then our test is Thursday, March 21st. Any last questions? Okay. Oh, yes.
I guess, like, so if you're not sure about, like, stationarity, I guess, like, could you just use, like, the unit root test?
That is another approach, too. You can. There's actually a hypothesis test that one could do. It's called the Dickey-Fuller unit root test. And essentially, to think about it, if we think of an AR1 model, I'm not going to write the alpha term in there. Think of what happens if phi 1 is equal to 1. Essentially, we have first differences then on the left side. And so what one could do is do a hypothesis test: is phi 1 equal to 1 or not? Now, you might be thinking, well, we're kind of doing it with that confidence interval there. Well, with the confidence interval, we do have a range. The problem with this here, and also in many other statistics applications, when you have a hypothesis test where something is on, let's say, the borderline of the parameter space. So let's say, for example, if you were to do a hypothesis test for is sigma squared equal to 0 in terms of sigma squared a variance. Of course, you can't have a variance of 0. Well, I guess you can. But, that's right on the borderline. And so because of that, you cannot use, let's say, if you're familiar with like a Wald test, you should be familiar with Wald tests. You shouldn't do that because the test will not work properly. A similar thing here can occur. And so there have been special tests called unit root tests, where the most popular one's the Dickey-Fuller test, that have been proposed to do a hypothesis test like that. Now, Andrew, I don't typically talk about that particular test in this class. Maybe we will, but we are at least doing an informal type of assessment for what the Dickey-Fuller test does. Okay, but thank you for bringing that up. Any other questions? Okay, that's all for today.